The sun delivers more energy to Earth in just 1 hour than the entire world uses in a year. But the challenge is, how do we capture and store that energy? One promising answer is photoelectrochemical water splitting. Hello, everyone. My name is Arjun Vemuri, and today I'll be presenting my literature review, Optimization of Solar-Powered Hydrogen Generation with Photoelectrochemical Water Splitting. This project explores how PEC water splitting works, what role semiconductors play, the latest innovations in the field, and why PEC is so important for building a clean hydrogen economy. Why hydrogen? The demand for clean and sustainable energy alternatives has never been more urgent. Fossil fuels are a major driver of CO2 emissions, and climate change is a global issue we urgently need to address. Hydrogen offers a unique solution. It's a clean energy carrier that produces only water when used. Right now, most hydrogen comes from fossil fuel-based methods like steam methane reforming or coal gasification, which is terrible for the environment, releasing up to 15 kilograms of CO2 for every kilogram of hydrogen produced. In contrast, photoelectrochemical water splitting, or PEC, produces zero carbon emissions. Hydrogen is especially valuable for sectors where electrification is difficult, like long-haul transportation, chemicals, and steel. It's also extremely versatile. It can power fuel cell vehicles, back up the grid, and be used in industries like ammonia production and refining. In the future, hydrogen will be critical for stabilizing renewable heavy energy systems. So what is PEC water splitting? How does it differ from other hydrogen production methods? It's a process that uses sunlight and water directly to generate hydrogen and oxygen. Unlike traditional electrolysis, though, which needs an external electricity source, PEC integrates light absorption and catalysis in a single device. This makes it simpler and potentially more scalable. Although still in the early stages, PEC is one of the only approaches that could enable a circular energy economy where we are able to recycle waste, minimize emissions, and directly store solar energy in the form of hydrogen fuel. So the first fundamental step is light absorption. When sunlight hits a semiconductor photoelectrode, photons with energy greater than or equal to the material's band gap excite electrons from the valence band into the conduction band, and this leaves behind a positively charged hole. These electron-hole pairs are separated and transported to the electrode surface, where they can drive chemical reactions. So the size of the band gap is really critical. If it's too small, the semiconductors absorb light efficiently, but it won't have enough voltage to split water. If it's too large, it provides enough energy for the reaction, but it wastes most of the solar spectrum. That's why the ideal band gap range is about 1.6 to 2.6 electron volts. Once charges are generated, they power the redox reactions at the electrodes. So at the cathode, we have the hydrogen evolution reaction, where protons combine with electrons to form hydrogen gas. And at the anode, the oxygen evolution reaction takes place, where water molecules are oxidized, producing oxygen gas, protons, and electrons. Together, these half reactions make up the overall water splitting process, using sunlight to generate hydrogen and oxygen gas. The third piece of the fundamentals is the cell design. A PEC system includes three main components: the semiconductor, which absorbs sunlight and generates charges, the counter electrode, which balances charges and provides reaction sites, and the electrolyte, which allows ions to move between electrodes. One way researchers boost efficiency is by using tandem cells. These combine two semiconductors with different band gaps. One absorbs high energy photons and the other absorbs low energy photons. And this setup captures a wider range of the sunlight and can achieve higher solar to hydrogen or STH efficiencies without needing any sort of an external bias or external voltage supply. So here on the left, we have a photoanode based cell, and in the middle, it's a photocathode based cell, and on the right is the tandem cell configuration. So semiconductors are really the heart of PEC water splitting. The photoanode is usually an N-type semiconductor that absorbs sunlight and drives water oxidation. And the photocathode, often a P-type semiconductor, drives the reduction protons to hydrogen. Um, and then the performance of these depends on three key properties, which would be band alignment, which determines whether reactions are energetically favorable, charge separation efficiency, meaning how well electrons are and holes are kept apart before recombining, and stability, since materials are constantly in contact with things like light, water, and electrolytes. Choosing the right semiconductor is essential to making PEC efficient, affordable, and scalable. So recent innovations are making PEC much more practical. The biggest breakthrough is tandem PEC cells, which have already achieved STH efficiencies near 19.3% in lab tests, and theoretical models suggest efficiencies above 30%, even up to 43% shown in the table with ideal materials. And for context, the US Department of Energy has set a 25% target as a benchmark for commercial PEC technology. And as you can see, we've already surpassed that in theoretical. And at the same time, researchers are shifting towards earth-abundant semiconductors, such as um, using bismuth and iron. And these materials are cheaper and more sustainable compared to rare elements like platinum or gallium, which efficiencies are lower with these alternatives and currently around 4% in recent tests, but they're far more cost effective and avoid supply risks. And this trade-off between cost and performance is one of the main challenges currently in scaling PEC water splitting. So what's next for PEC? If optimized, photoelectrochemical water splitting can decarbonize industries where emissions are hardest to reduce, like steelmaking, chemicals, and long-haul transportation. It could also provide long-term energy sources, stabilize renewable heavy power grids, and supply clean fuel cells for hydrogen-powered vehicles. Imagine going in a plane powered by hydrogen or riding a ship powered by hydrogen. Scaling PEC is still challenging but advances in tandem cell designs and materials researchers are pushing the field closer to practical applications. So to conclude, PEC water splitting is a promising pathway to clean hydrogen production by combining light absorption and catalysis in a single integrated system. It offers a simpler and potentially cost-effective solution compared to today's fossil fuel-based methods. While challenges remain with efficiencies, um, ongoing research has already achieved nearly 20% efficiencies in labs and shown real progress using affordable, earth-abundant materials. Looking forward, PEC could play a central role in building a sustainable hydrogen economy and supporting the global transition away from fossil fuels. Thank you for listening.